Hello, my name is James Mara. I'm an electrical engineer.
I'm Asher Danielson. I'm a mechanical engineer.
I'm Jaden Kalber. I'm an electrical engineer.
I'm Mason Herchek. I'm a mechanical engineer.
And we are Group 4, also known as Bright Descent, and our project is the gravity lamp. The target of our project is to create a lighting source that is powered by its own gravitational energy. Here is the block diagram for our team's project. The blocks in orange represent the spool and housing subsystems. A rope connects to a spool that generates rotational energy as it unwinds. This rotation feeds into a one-way ratchet bearing inside the spool, which engages and turns off the gear train. All these components connect to the housing subsystem through internal mounting points. The housing stores all of our subsystems, separating the electrical components from the mechanical components that will be exposed to water. This separation is crucial to prevent water from reaching the electrical subsystems, which could fry the circuits and cause a failure of vital project functions. The next subsystem is the gear train, which is shown in red, that converts the torque applied to the spool to the appropriate torque to drive the generator when charging. These two subsystems allow us to convert linear motion into rotational motion. In purple is the power generation and storage subsystem. The purpose of the power generation and storage subsystem is to ensure that our battery is being sufficiently charged and is supplying sufficient amperage and voltage to power the rest of our electrical components. The load/charge controller is the central component of the system, handling the power input from the generator, which is connected to the gear train, and the power input from the wall, which is connected to an AC to DC step-down component and a buck booster, which steps up the input from 5 volts to 9 volts. Both of the power inputs are then fed into the battery. As for the lighting subsystem, seen on the right, its purpose is to provide at least 400 lumens to meet our project specifications. Just before the light, there is a switch to turn the LED on and off. The final subsystem shown in green is the controls and user interface subsystem. The purpose of this subsystem is to monitor the electrical performance of the gravity light and provide feedback to the user. At the center of the subsystem is the Arduino Nano R4, which communicates with the current sensors and OLED display using I2C communication. The sensors monitor power entering and leaving the battery, allowing the Arduino to calculate battery status and charging performance, and estimated runtime. The subsystem also includes 2 switches. One controls power to the monitoring electronics, while the other controls power to the LED light. This information is displayed on the OLED screen in real time. The control subsystem is powered by the battery through a 5-volt buck boost converter, which provides a regulated supply for the Arduino and display.
Our entire design is dependent on a master geometry document where the relative locations of major components and their sizes are dictated. With the CAD set up this way, I designed the gear train so that the generator, which is the heaviest component in our system, sits below the spool to keep the center of mass below the point where the system hangs. The gear train has a train value of 81.3 because this would drive the generator at an optimal RPM when charging the battery. Spacers are used between the housing and generator to allow for adjustment of the generator's location relative to the gear train so the gears mesh properly.
Given our housing specifications, size and weight were critical considerations throughout the design process. The housing needed to fit within a volume of 15 to 30 liters while also maintaining a total weight below 11 pounds. To meet these requirements, we selected compact, lightweight components whenever possible. For the housing and gear train, we chose PLA because of its low weight and ease of manufacturing. As Asher mentioned previously, the generator is our heaviest component in the system, so making weight reduction in other areas was especially important. Weather resistance was another key design requirement given our specifications, so the housing needed to prevent water from reaching electrical components when exposed to natural elements like rain or even water sprays. So to do this, we did a water spray at angles of 60 degrees from vertical, giving an IP rating of 3, and also needed to test withstanding vertical falling rainwater, giving an IP rating of 1. To satisfy these protection requirements, I designed a dedicated compartment for the electrical components. This compartment houses the circuitry responsible for directing power from the generator, displaying system readings, and powering the light source. By isolating these components with a protected enclosure, the design improves reliability and reduces the risk of water-related damage during operation.
The circuit diagram shows the full electrical layout for the gravity lamp. On the left side, the generator and wall charging path both feed into the solar charge controller. Each input has its own current sensor, so we can monitor power coming from the generator and from the wall charging circuit separately. The charge controller manages the 3.7 volt battery and sends power to the load side of the system. From there, the load output goes to the third current sensor, which measures the power being delivered to the LED light and the Arduino control subsystem. The Arduino subsystem is powered through a 5-volt buck-boost converter. The Arduino Nano R4 communicates with the OLED display and all three current sensors using the shared I2C bus. The OLED then displays system information such as voltage, current, power, battery status, and the estimated runtime.
Now for our summary of our final test plan results, starting with performance and capability. All of our specs passed as our light was able to produce over 800 lumens, and we were able to get efficient and clear readings from our OLED display.
For the user interface requirements, our system was designed to provide the user with useful information while keeping the controls simple. The OLED display shows important system data such as battery status, charging information, and estimated remaining time. Runtime is calculated using real-time current measurements from the battery output sensors and the known battery capacity. The system is also ready to produce light immediately as long as the battery has stored energy, which exceeds our requirements of being ready within 10 minutes from a fully stored state. Finally, the user interface remains simple, using only 2 rocker switches to control the system operation, which is well below our maximum requirements of 5 user controls and meets our desired targets of 2 or fewer controls.
Next, for our size specifications, we were able to meet all of our specs as our housing was not larger than 12 inches in any dimension and came out to a total volume of 7.74 liters and was also within weight specification of only being 9 pounds. Finally, for our safety, construction, installation, and sustainability, all of our specs were met except for our systems material component list, as we went over our budget of $300 due to electronics failures and needing extra hardware.
Through these solutions, we have managed to make 3D printed parts that fit our components without significant modifications or post-processing. We also made a functional 3D printed gear train with minimal mechanical losses, a 3D printed housing that supports the gear train with a 45-pound load applied, and a watertight enclosure to house most of our electronics.
Throughout this project, we faced many challenges. One of the biggest challenges we faced was integrating multiple sensors and devices onto the same Arduino while maintaining a reliable communication and electrical connection. This required soldering components onto a perf board, configuring unique I2C addresses for each current sensors, and troubleshooting communication issues between the sensors and the OLED display. Another challenge was preventing reverse current from causing the generator to act like a motor, which we solved by adding a Scotchy diode to the charging circuit. Through these solutions, we successfully integrated all 3 current sensors on a single I2C bus, developed a battery-powered monitoring system using the Arduino R4 and OLED display, and implemented real-time monitoring of charging power, battery output power, and estimated runtime for the gravity light system.
While doing this project, we developed proficiencies with advanced Onshape tools to improve CAD modeling, efficiency, and accuracy. Utilize the Derive tool to reference geometry and sketches from existing parts, reducing repetitive modeling work and maintaining consistency across components. Also, how prototyping helps to find design flaws. Along with learning how to effectively research electrical components by referring to their data sheets. And finally, we gain proficiency when it comes to troubleshooting and testing electrical connections within physical circuitry. In this video, we are demonstrating our project's functionality when it comes to generating power from falling. Here is also a demonstration of the functionality of our user controls.